Today's lesson is on proving triangles similar because, of course, you know that in each unit we want to move toward being able to prove things. And this is similar to, no pun intended, back when we were learning about congruent triangles. You remember how we first had to show that all the corresponding parts were congruent, and then we got the shortcut postulates and theorems like angle, side angle, and all those that helped us to have some shortcuts to prove that triangles were congruent. Well, we got the same kind of thing with similarity. So here we go. The first one we have is an angle-angle similarity postulate, and we're going to call it AA, and we are going to put our little similarity symbol there since we want to be able to distinguish between similarity and congruence. And this postulate says if two angles of one triangle are congruent to two angles of another triangle, then the two triangles are similar. And of course we could prove this if we wanted to or needed to, but I'm going to spare you that in these lessons. We might have a homework problem or two to prove some of these, but for now we're just going to accept them. So what we know here is if that angle K is congruent to angle Y in that triangle, angle J is congruent, wait, J? There's no J. Oh yeah, J right here, sorry, J right there. Angle J is congruent to angle X, then what I know is that triangle JKL is similar to triangle XYZ. And again, order matters when we're making a similarity statement. All right, the next theorem that we have is the side-side-side similarity theorem. Very similar to the side-side-side congruence theorem. It says if the lengths of the corresponding sides of two triangles are proportional, then the triangles are similar. So here I can see that the ratios of all the corresponding sides, if they're all equal, then I know that triangle ABC is similar to triangle PQR. Side, side, side. Okay, now we got another one. Side, angle, side. So the side, angle, side similarity theorem. So the last two are theorems. First one's a postulate. It says if an angle of one triangle is congruent to an angle of a second triangle and the lengths of the sides including these angles are proportional, then the triangles are similar. So if angle X is congruent to angle M and those corresponding sides that include those angles are proportional, then I know that triangle XYZ is similar to triangle MNP. Order matters. Don't forget that. Okay, so of course we got some examples. I think the whole rest of the lesson deals with examples, so if you want to stop right now and try to do all these by yourself, knock yourself out. I'll go through a couple and then I'll pause and let everyone do the rest. Okay, so the question is triangle ABH similar to triangle KLH? Well, we know that angle B is going to be congruent to angle L because of the right angles theorem, and of course we'd have to state that in a proof if we were doing a proof. And we know that these two angles are congruent because of the vertical angles theorem. So by angle-angle, the angle-angle similarity theorem or postulate, we do know that yes, triangle ABH is similar to triangle KLH by angle-angle similarity. Easy, right? Okay, which of these triangles are similar? Okay, well we got quite a bit of work to do here because of course we're going to be using side, side, side if any of them are similar because we don't have any information given about the angles. So first let's start with triangles KLM and triangle GHJ. And what we're going to do is we're going to set up ratios comparing all the corresponding sides, and if all those ratios are equal, then we know that those two triangles are similar. So for KLM, let's see, so we're going to do let's start with the longest side in each triangle first. So KL over, that's the longest one there, NP, I guess. I'm not sure that order is correct, but we'll just play it by ear for the moment. So if KL over NP is equal to the medium side, LM over PO, I'm going to say. Again, not sure that's the correct order, but I need the links right now more than I'm concerned about the order. So, and finally the short sides would be KM over NO. So let's see what those ratios are. KL is 20, NP is 25. Does that equal LM, which is 16, over PO, which is 20. Wait a minute. That might be a Q. I don't know. KLM. Ah, I'm doing the wrong triangles. Let me fix this right here. This isn't triangle GHJ. This is triangle NPQ, and that should be a Q. NPQ. There we go. Sorry about that. KLM and NPQ. So I got 20 over 25, 16 over 20, and finally KM. KM is 12, and NQ is 15. Let me simplify all those, and let's see, 5 goes into that 4/5. 4 goes into that 4/5. 3 goes into 12. 4, 3 goes into 15. 5. So yes, all those are equal. So I know that triangle KLM is similar to triangle NPQ. Okay, and that's what you're going to have to do for the other sets. You're going to need to do that for triangle KLM and GHJ, and you're going to need to do that for triangle GHJ and NPQ. And what you're going to find is that the other two sets are not similar, so I'll leave you to do that on your own. So you're going to check on your own triangle GHJ and NPQ. And I'm going to tell you right now, they're not similar. But I do want you to do this for the exercise. And then you're going to check triangle KLM and triangle GHJ. Those are the two sets I didn't do. And once again, you'll find that those are not similar. But do practice that. All right, how about these two? Well, you can see I got a little triangle that's inside of another triangle. Okay, so you know what? I can see right away that those two are similar. You know why? Because I've got these two angles here that I know are congruent. Oh, and by the way, I forgot to put this up here. This is by side, side, side similarity. It said explain, so there's my explanation. Okay, so DFR is the big triangle, MNR is the little triangle, so the two red angles are right angles, so of course they're congruent, and look, they both share that angle R, so yes, triangle DFR is similar to triangle MNR by the angle-angle similarity postulate. I don't even have to mess with those side links, right? Because I got the two angles, the two corresponding angles that are congruent, two sets of corresponding angles, I don't have to worry about the proportional sides. That is a nice shortcut there. Okay, how about this? Describe how to prove that triangle RSV is similar to YXV. Well, I got two sets of corresponding sides, and I got these angles, right, vertical angles, so it looks like I'm going to have to use side angle side, but first I got to check to make sure the corresponding sides are proportional. So in other words, is 20 over 24 equal to 15 over 18? Let's simplify those. That'll be 5, and let's see, 4 goes into that 6, and if I divide 3 into each of these, I get 5, 6. So yes, they are similar by side, angle, side, similarity theorem. Okay, so that's how you would prove it. So in the proof, of course, you would have to have a step saying that the angles are congruent by the vertical angles theorem, and then you'd have to have a step setting up the ratios of the corresponding sides, simplifying them, and showing that those sets of corresponding sides are proportional, and then you could say that those triangles are similar. Okay, what do we got now? Oh, a real life problem. To comply with Americans with Disabilities Act, wheelchair ramps made for new construction must have a height to length ratio of 1 to 12. 1 to 12. And the new construction, the height h to the bottom of the door is 2.5 feet. Use the proportion a over b equals h over r. So I'm going to write that here. To estimate the length r that the ramp needs to be to have the correct ratio. In the proportion, use a equals 1 foot and b equals 12 feet. So I'm going to go ahead and substitute that in. 1 over 12. Okay, and they give us something else. The height is 2.5 feet, and all these are in feet, so it's okay if I leave my units out right now. The height, so I'm going to plug in 2.5, and I'm trying to find the length r that I need that ramp to be. So you know what I'm going to do here? I'm not going to get out my calculator. What I'm going to do is I'm going to change this 2.5 to a fraction. So let me come over here and do that. So I have 1 over 12 equals 2.5 is 5 halves over r. So now it's easy for me to cross multiply. So I can get r equals 12 times 5 halves, and of course that cancels with that and gives me 6. So that means the length of that ramp has to be at least 30 feet. Has to be 30 feet long for it to meet the ADA requirement. All right, real life problem there. When would I ever use this in real life? Right there, right there. Okay, here's another one. You know what? Pause right here and you try to do this one. This is a fun problem that you're trying to use a proportion to figure out how tall the Washington Monument is. So pause here and come back and check your answer. As always, we're going to draw us a lovely diagram here. So what we got is it says at a certain time of day, a 5'6" person standing next to the Washington Monument casts a 4-foot shadow. So here's our 5.5-foot person, and I put in 5.5, and then here's the shadow, or hers, 4 feet, and it says at the same time, the Washington Monument, which is right here, as you can plainly see, casts a 400-foot shadow. So here's the shadow of the monument, and it says, using your knowledge of similar triangles, similar polygons, similarity proportions, determine how tall the Washington Monument is. So I really need this picture here to help me figure out how to set up my proportion. And once I have that, I'm good to go. Please draw the picture. Okay, so I set up my proportion. I know the height of the monument is to the height of the person, and that's this part right here. And you know I don't like to work with decimals because I don't have a calculator, so I'm going to change that 5.5 to 11 halves. The height of the monument is to the height of the person, as the shadow of the monument is to the shadow of the person. So there's my proportion, and then I just take off and cross multiply. Don't need to switch the means or extremes or anything, because 400 over 4 simplifies very nicely to 100 over 1. And then when I solve that proportion, I end up getting that the Washington Monument is 550 feet tall. And for all you history buffs, the actual height of the monument is 555.5 feet. So this is an approximation, but it's a pretty dang good one. And it's really interesting if you are interested in things like this, if you will read up on why that's the height of the Washington Monument. I think you'll enjoy that bit of history. So that's it. Please summarize your lesson at the bottom, and we'll see you next time.